Mars is an unforgiving planet. No spacecraft that dares to enter can escape the curse of the red planet. Throughout history, more than half of all missions attempting to land there have met their doom. Named after the bloodthirsty Roman god of war, Mars has earned its reputation as the spacecraft graveyard, and at the heart of this curse lies the Martian atmosphere, a treacherous thin veil that makes safe landings nearly impossible. Yet, despite all this, we want to send people there, which is clearly impossible with today's technology. But what if I told you that some engineers believe that they have found the secret to breaking this curse out of thin air? What they've been working on might just blow your mind. So we want to go to Mars. Eventually. But we need a lot to survive on another planet. We need a vehicle to take us down to the surface and leave it. We'll also need shelter, a life support system, food, water, breathable air, or technologies to let us at least harvest some of these things from Mars. So crewed landings on Mars, or at least landing the infrastructure required, will be massively heavier than the robots that we currently send there. So that means the landing technology for the Mars missions will not be a much bigger version of the landing technologies that we currently use. It is a whole new puzzle. To land on Mars, we need to get smarter, like how you can land and that subscribe button to get smarter from my space videos. And don't forget to click on the bell icon to stay in the loop. If a planet's atmosphere is thick enough, an incoming spacecraft, typically entering at approximately 25 times the speed of sound, would heat up. Many people out there would tell you that this heat is a result of friction between the spacecraft and the atmosphere, but that is not entirely correct. This heat actually comes from the compression of gases from the spacecraft, and when gases compress, they heat up. As the vehicle punches through the atmosphere at hypersonic speeds, it compresses the gas to thousands of degrees, heating up its surface to almost 2,000 degrees Celsius in the case of Earth and Mars entries. And that is just the first problem. On Earth, the atmosphere is thick enough to be used to decelerate a spacecraft and for parachutes to work, but they're much less effective on Mars, where the density of the atmosphere is 1% of Earth's. Parachutes alone are not enough, and historically, rocket engines are also needed to further slow the spacecraft down. For earlier Mars rovers, even this is not enough, so airbags were used to absorb the impact during touchdown. But as missions progressed and we get larger rovers like Curiosity and Perseverance, engineers needed to come up with a new solution because airbags were no longer practical. So what did they come up with? Rocket-powered sky cranes. Like, who even thinks of strapping a Mini Cooper to a set of rocket engines and having it dangled beneath a set of wires? And a room of equally crazy engineers looked at the idea and were like, yup, that'll work. We can see that it just gets inherently more complex as the missions get bigger. And there were landing side limitations too. For the largest payload sizes we've sent to Mars, we can only land on lower altitudes below Martian sea level. Higher than sea level, we crash. In a nutshell, the Martian atmosphere is thick enough to screw you over, but too thin to help you out.
You, Mars.
So the Perseverance rover has been the heaviest thing we've landed on Mars, which weighs approximately 1 metric ton. But NASA engineers have estimated that we need to land at least 20 times that mass for a human mission. Propulsive landings require a lot of fuel, and more fuel means more mass, which is the tyranny of the rocket equation. Comically large parachutes larger than football fields are definitely not an option. So what we can do is slow the spacecraft down early on to increase the amount of aerodynamic drag experienced by the spacecraft at a higher altitude by increasing its surface area, which has to be so large that it can't fit inside a rocket. So the solution is to make a packable, lightweight, multifunctional heat shield that offers thermal protection, stability, and deceleration of payloads, which can be stowed to fit inside a rocket and would deploy to its full size just before entry. And these packable heat shields are very different from traditional rigid capsules or aerosols. The rigid aerosols of today consist of a heat shield and a back shell to cover and protect the payload. The heat shield is made of ablative materials or sacrificial materials designed to burn away at high temperatures to protect the aerosol. The large surface areas offered by packable heat shields means that they provide reduced heating environments compared to rigid aerosols, so they don't rely on ablation as much and back shells are not necessary, which would save some mass. But they still face significant heat as everything traveling at hypersonic speeds do. So they are made of high temperature flexible fabrics or composites that are thinner and lighter than traditional rigid heat shields, and in some design choices, coated by a thin ablative layer. There are two ways about a packable heat shield. The first is to fold it so that it deploys mechanically. Examples include the ADEPT project being developed by the NASA Ames Research Center, which opens up like an umbrella, and the Prudwin origami heat shield by the UK-based company Spaceforge. The second is the use of an inflatable structure, which is our focus for this video. Inflatable heat shields are also known as hypersonic inflatable aerodynamic decelerators, or HIAD. They have a better scalability potential than a mechanically deployed heat shield and also save more mass and volume. The idea of inflatable heat shields is not new and can be traced all the way back to the 1960s. It was a significant element of the 1962 Roost project, the reusable one-stage orbital space truck. Roost was a reusable single-stage-to-orbit launch vehicle concept designed by the Douglas Aircraft Company using conventional liquid hydrogen and oxygen-powered rocket engines. The heat shield was divided into an upper torical section and a lower conical section. Following payload release, the shroud protecting the upper section would be jettisoned. Leftover liquid hydrogen would be heated by solar radiation into a gas, which would slowly inflate the upper section ahead of re-entry to prevent it from exploding. The lower section would be packed in a cylinder surrounded by the engines, inflated by 8 helium tanks positioned inside the liquid hydrogen tank. The heat shield would be made of a wire cloth made of a nickel-based high-temperature alloy or stainless steel, coated with a silicone sealant. Even wilder was a 1963 study by General Electric called MOOSE, which originally stood for Manned Out of Space Easiest, but was later changed to Manned Orbital Operations Safety Equipment. Now, this was an insane idea for military space programs like the Dinosaur Shuttle or the Manned Orbiting Laboratory to let astronauts bail out of orbit should anything wrong happen to their spacecraft, and no other rescue options are available. So this was basically an extreme emergency measure. The idea was that an astronaut would grab a MOOSE pack, eject out of the spacecraft, pull a ripcord, and the heat shield would inflate not with air, but with polyurethane foam. Small handheld thrusters would be used to position the astronaut, and a solid rocket engine would fire from a chest pack for the re-entry burn. Look, when people say that early astronauts had the right stuff, I'm pretty sure that the right stuff included balls of steel, but any person in their right mind would be crapping their pants at the sheer thought of literally falling from orbit protected by nothing more than a spacesuit and a layer of foam strapped onto their backs. The Gundam Motor Suit Z anime from the 1980s actually popularized this concept and most likely drew inspiration from the MOOSE project. Inflatable decelerator studies for Mars atmospheric applications began as early as December 1965 when the Goodyear Aerospace Corporation investigated multiple designs under a contract for the NASA Jet Propulsion Laboratory. But these studies were not exactly inflatable heat shields, but rather supersonic decelerators after entry and peak heating took place. Now, this is where I'll make the distinction between a HIAD and an IAD, an inflatable aerodynamic decelerator, because not all IADs are HIADs and can only operate in a supersonic regime. The NASA Langley Research Center later tested a wind tunnel model of the Goodyear's attached body decelerator concept, where the decelerator is directly attached to the aeroshell. These models deployed successfully at supersonic speeds of up to Mach 4.4. And these studies were performed for application to the Voyager program, and I'm not talking about our favorite interstellar scouts, but a program planned in the 60s to send a series of probes to Mars using Apollo-derived technology, including a Saturn V. But that's a story for another day. The cancellation of the Voyager Mars program evolved into the Viking program, and the name Voyager was of course carried on to the interstellar probes that we know and love. But because of the higher performance and classic disc gap band parachutes at a wider range of supersonic speeds, they were also considered for the Pioneer Venus mission and even the Galileo mission to Jupiter, till later studies showed that the Viking program did not need parachute deployment above Mach 2, and that Earth-based parachutes would work for Pioneer Venus and Galileo. So that basically killed further development on inflatable accelerators in mid-1970s America for quite some time. Then in 1996, the Russians were ready to test inflatable decelerators operating as both heat shields and deceleration devices in the Martian environment when they sent 2 penetrators using their inflatable reentry and descent technology, or IRDT, on the Mars 96 mission. Unfortunately, a launch vehicle failure led to the loss of the mission, and we never got to see it happen. Meanwhile, the European Space Agency was interested in the IRDT as they saw potential applications for it in the Earth orbit environment, like returning payloads from the International Space Station, so they collaborated with Russia to further develop this idea with a series of demonstrators that they did not have the best of luck with. The IRDT consisted of 2 sections. The lower one, consisting of a series of stacked toroids, would deploy first as a heat shield and was coated by an ablative material, followed by the upper section for further deceleration. During the first demonstration, which was the only orbital test, The first heat shield section worked well, but the second section did not inflate properly, so it hit the ground too fast and the spacecraft was partially damaged from the crash. The second version was a suborbital demonstration, and both of its test flights were unsuccessful as it failed to separate from the launch vehicle in the first, and the second was lost, likely at peak deceleration. So with these further European developments, an improvement in materials, and a more serious interest in more challenging and heavier interplanetary missions, naturally, the American interest for HIADs picked up not long after that. And NASA's HIAD project uses a stacked Torah design building on the IRDT lessons. For this, they developed a series of demonstrators for the IRV missions, which stood for Inflatable Reentry Vehicle Experiment. The first of these suborbital missions took place in 2007, but the experiment failed to separate due to an anomaly on the Terrier Orion-sounding rocket. A second successful attempt was made in 2009 on the IRV-2 mission, which led to the IRV-3 mission in 2012. Among its upgrades is a steering system which worked by shifting some mass side by side to tip it over. Weighing a total of 281 kilograms, it also featured a larger center body structure that houses the inflation system and instrumentation. A heavier system meant an increased heating environment, which was done to test the materials used. The inflatable structure itself is made of silicone-coated Kevlar, shielded by a thermal protection system, or TPS, consisting of 3 primary layers. The outermost layer in pink is made of a Nextel 312 cloth, followed by an insulation layer made of aerogel, and a polyamide film that acts as a barrier to prevent gases from penetrating the TPS. During a successful 20-minute flight, IRV-3 withstood loads of over 20 Gs and temperatures of 537 degrees Celsius before splashing down on the Atlantic Ocean. In November 2022, NASA launched another demonstrator twice the diameter of IRV at a total mass of approximately 1 metric ton, making the largest HIAD ever tested. The test was orbital and was named LOFTED, Low Earth Orbit Flight Test of an Inflatable Decelerator. It experienced hypersonic speeds above Mach 25 and surface temperatures of nearly 1500 degrees Celsius. A massive success, Lofted was recovered at the Pacific Ocean after the 2-hour-long test and significantly paved the way for future designs. In this decade, we have also seen increased international interest in HIADs. China attempted to launch their very own in May 2020, which failed after 19 hours in orbit. Europe has decided to mature their inflatable heat shield technologies with funding from Horizon Europe, which began with the Vesta 1 and 2, and now the Icarus project, primarily meant to recover rocket stages from space. Icarus kicked off last year and aims to test its first demonstrator in 2028. Led by Spain, other participating countries within the Icarus consortium are Germany, France, the Netherlands, and Italy. Among its most notable partners is the German company Atmos Space Cargo. It started developing the Phoenix capsule to return cargo and life science experiments from orbit, which uses an HIAD as a heat shield and a descent system. With inflatable heat shields being developed around different corners of the world today, I believe that we are getting closer to putting our first steps on Mars. If you enjoyed this video and learned a thing or two from it, please don't forget to like, comment, and subscribe for more videos on space history and technology. And I'll see you in my next video.